talk about graphing some rational functions. I've got the rules that I use. Excuse me. I've got the rules that I use here. I'm going to go ahead and flip through a few slides. You may want to pause at those slides. I'm not going to waste a lot of video time going through each of these steps. So feel free to pause. I'm absolutely going to be going through the process here. So I think this is going to make sense for you. So let's take a look at the different slides for each of these three processes, which I guess you could claim as five processes. Again, might want to pause. I'm not going to talk through these. I'm just going to have them on for a couple seconds. If you want a downloadable version of this, it's on my website. That would be, you could Google and find it by typing in purple shirted nerd, one word, purple shirted nerd, one word. There'll be a link to a Hananiga High School website, and this is section 2.7. You'll find it for sure. So here they are the rules I'm going to be explaining shortly through four examples. We set the numerator equal to 0. Again, you might want to pause this if you want to read it. We set the denominator equal to 0. That's going to give us some information about our graph after we solve that. We make certain to check and see, are any of my numerator zeros and denominator zeros common? In that case, we have a special situation where we have holes in our graph. You'll see examples like that. We set x equals 0, which gives us the, and solve, that gives, or simplify, that gives us the y-intercept of the graph. Here's the big X test. This one is one that really is going to make a lot more sense when I explain it during a problem. But again, you may want to pause at this point and read through that. And freshman graphing, that's just t-charting. I just refer to it as freshman graphing. It's kind of a starting point. Get a bunch of points on, try to fit a curve to it. Okay, so I have each of those, kind of fighting a cold here, so bear with me. I have all of my rules on each of the next four examples, just kind of as an outline for what I'm going to be doing here. And the first thing I do when graphing a rational function, and of course a rational function is just a rational expression could be just a fraction. And a rational function could be a polynomial on a polynomial. So the first thing I do is 1a, I set the numerator equal to 0, and I solve that. So we quickly get x equals 1/3. And we all know if the numerator of a fraction is 0, the fraction is equal to 0, unless the denominator is also 0. And we'll see an example like that soon. But if we end up with 0 on 0, I refer to that as the outstanding movie Ghostbusters. In Ghostbusters, there was a scene, the guys capture these ghosts with these nuclear accelerators, and there's a scene, I believe it's Bill Murray or Dan Aykroyd, one of the two explains never to cross the beams of these nuclear accelerators. The world will cease to exist as we know it. And that's kind of the 0 on 0 is the mathematical equivalent of crossing the stream. So we got a test for that, but probably 1/3 is a 0. So test B, we set the denominator equal to 0. 1 minus x equals 0, and it would be more apt to say we state that the denominator cannot equal 0, therefore x cannot equal 1 because we cannot divide by 0. And now we do a quick check. Are any of our numerator zeros equal to our denominator zeros? No. So I'm ready to graph at this point. So I have a 0 at 1/3. So at about where 1/3 would be, I'm going to put a 0. And B, x cannot be 1. Excuse me. So if x cannot be 1 at 1, I've got a vertical asymptote. My graph can't touch that. And most of you have probably worked with asymptotes before, and I can usually elicit this response from a class. I said, okay, guys, you've worked with asymptotes. What's your real feeling about asymptotes? Come on, we're one happy family. You can say it. No discipline referrals. What do you think about asymptotes? What do asymptotes do? And inevitably, I can get a student to either mumble it or out loud just say, asymptotes suck. And I said, boy, That's exactly right. That's not a word I'm crazy about using in a classroom environment, but that's what they do. They suck curves in toward them. So finding asymptotes gives us a lot of guidance what the curve's going to look like. Okay, C. I just set x equal to 0 in my function, and in this case, I get 1 minus 3 times 0 on 1 minus 0, or 1 on 1, which is pretty evident because if we cross those terms out, make them 0, it's just 1 on 1, which implies, of course, that 0 maps to 1. 0, 1 is an ordered pair. So 0, 1 is on the graph. So it's just that's just part of that. Really, truthfully, is a freshman graphing technique, but it's so easy for 0, and often we want to have the y-intercept. Okay, here's a biggie, the big X test. Reading back through that, backing up the video, is going to make some more sense after we go through 4 examples. But here's what I do. I say, what happens when X gets big? Like, for instance, what happens if X is a billion? If X is a billion, the numerator becomes 1 minus 3 billion. And if I gave you $1 and took away 3 billion, that pretty much makes that $1 insignificant. So the 1 in the numerator, pretty insignificant. The 1 in the denominator, pretty insignificant when X gets really, really big. So our step 2, big X, this graph is going to eventually, when X gets big, try to mimic negative 3x on negative x when the ones become insignificant, which of course is just 3. The graph wants to reach a height of 3 when x gets huge. It never quite will, but it's going to get closer and closer and closer. Part of the big X test I like to talk about is I like to look and say, well, we're dealing with a first degree divided by a first degree, a 0th degree. We don't typically talk about 0th degree polynomials, but here's one. 5x to the 0th, which of course is 5 times 1. A 0th degree is just a constant. This graph wants to be a constant. First degree divided by first degree, 0th degree, it wants to be a constant, and the constant that it wants to be is 3. So the graph is going to get sucked up to 3, which, to be honest, I think I've got enough information to know what's going on the left side of this graph, but we'll get back to that in just a minute. Okay, so step 3. What's going on here? I got some guidance. I've got 2 points here and here. I've got asymptotes that are going to suck those curves to them, and we look like this. I do not let the graph escape from the asymptotes. It gets closer and closer and closer to. I never pull it away from the asymptote. I want the viewer to know what's happening there. The graph is starting to mimic the line 3. Y equals 3. The graph, as I move to the right toward x equals 1, is starting to mimic the line x equals 1. Okay, now what I do need to know is what's happening to the right of 1. Maybe I have a curve up here in region A. Maybe I have a curve down here in region B between the with the guiding asymptotes. Now, if we really, really understood what happened up here in step A. Step A, everybody gets this. We found a 0. We found this 0 right here. But what you also need to get, and maybe even more importantly, is not only is 1/3 a 0, there are no more zeros. So there is no way I have a curve down here because it would have to get sucked toward this asymptote. It would have to have another 0 there. It can't exist there. It must be up in region A. I would just like to know how high. So I think I'm going to put the value 2 into my function. That's part of step 3, freshman graphing. So I put in 3, and I get 1 minus 3 times 3, all on 1 minus 3. I get negative 8 on negative 2. I get 4. So 3 gets me up to 4. And I am up in here. Is that right? If I put 3 in there, I get 9. I get negative 8. Yep. 3 gets me up to 4. And I've got a function that must be up in here. Okay. So is that actually 3? That was actually only over to 2. My apology on that. I knew something seemed a little bit wrong with that. It should have been a little bit higher. There's 1, 2, 3. This was 1/3. So we're really just a little bit higher than that. We're really up in here. Okay, so there we've got it. You may want to put in a value here, -1, and see what happens so we can try to control our height over here. It's just a matter of how exact you want to be, but we have a pretty darn good idea what the graph of this looks like at this point. Okay, let's move on to maybe a little bit more interesting function. All right, so we're going to go ahead and start this guy. I do notice that the numerator, for whatever reason, has been factored. Maybe that's nice, but it might be 5x plus 20. I notice the denominator could be factored. Maybe I'll do that. X plus 4, x minus 3. It might be helpful to look at that. I'm going to go with A. A, for the numerator to be 0, or 1A, my first 0 test, then 5x plus 20 must be 0, or 5 times x plus 4 must be 0. So x is -4, and I expect -4 to be a 0, but I'm not plotting it yet. B, set the denominator equal to 0. X plus 4 times x minus 3 equals 0. Should really be not equal 0, therefore x cannot equal -4, and x cannot equal 3, and there we have it. And boy, I hope I remember. Right there tells me there is a hole in the graph, and I might make a notation on the graph just so I don't forget to show that. If I put -4 into G, I get 0 on 0. I've crossed the beams. That does not mean there's a 0. It does not truly mean there's an asymptote. It just means the graph's going to just cruise along like it's going through x equals -4, stop, and start on the other side. So we'll take a look at that soon. But what I did learn is that x cannot be 3. Therefore, I have a vertical asymptote at 3. And I might come back here, -4, 2, 3, 4, and maybe I will just put in temporarily an arrow right there to remind myself at that value, because I forget this too. Okay, C. For problem number C, I'm going to have x equals 0. And if x equals 0, take a look. I get 5 times 0 plus 20 over 0, 0, minus 12, which means we have a point on the graph. When I put in 0, I get out, divide by 4, 5 on -3, or -5/3. So there's -3/3, -6/3. I've got a point on my graph somewhere right down in here. Okay. For 2, this is a little more conceptual, the big X test. When I put big values in x, I'm going to put it right here. Big values for x, like 1 billion, I get 5 billion plus 20. In the denominator, and 5 billion's a lot, no denying. In the denominator, though, I get 1 billion squared plus 1 billion. And I like to ask, do you really know how many billion? I mean, I've got 5 billions up top. How many billions do I have in the bottom then? 1 billion squared is 1 billion billions. Making 5 billions really insignificant. So if we think about this, the denominator as x gets big is just whipping the numerator. So I end up with a relatively small on a relatively big value, and the bigger x gets, the more that discrepancy becomes. Or I like to say I've got 1 apple to feed the world. How much does everybody get? It's definitely approaching 0. You'll also hear of just a rote rule that says if the degree of the denominator is bigger than the degree of the numerator in a rational function, then the graph is going to approach 0. So I have another asymptote right here. Okay. At that point, I think I have enough guidance on the left-hand side of 3 to know what's going on, but I'm going to go ahead and include in my t-chart. I think I'm going to put 1 in for x. It's so convenient just to know what's happening close to the y-axis. Excuse me. So when I put 1 into the numerator, I get 5 times 1, 5 plus 20, 25. 1 into the denominator, I get 1 plus 1 minus 10, negative 10, so negative 2.5. So I am down. Let's go ahead and extend this. At 1, I'm down to negative 2.5. That's exactly what I think is going on here. And I'm coming along this way toward my, boy, I almost forgot as it is, toward my negative 4 value that's a hole, and I need that hole represented on there. Okay. If you were to graph this function on your graphing calculator and you did, for instance, second calculate value and you entered negative 4, it would say x equals negative 4, y equals, and there would be a big blank there. It wouldn't know what to do. Trace right, trace left from there, and you'd pick up values, but there would be nothing at negative 4. Okay, now to the right, am I in A? Am I in B? I don't know, so I'm going to go ahead and get a little guidance. That's what freshman graphing's for. I'm going to put 4 in. Let's see, when I put in 4, I get in the numerator 5 times 4, 20 plus 20, 40. In the denominator, 16 plus 4, 20, minus 12, 8. So 4 gets me up to 5. 4 gets me up to 5. There's my guidance point. I know I'm up top here. And let the asymptote suck the curve into it. And there we go. Probably should have made that curve red. Okay. Let's take a look at this guy. We'll just go right down the line. We're going to get a little different discussion on the big X test here. But 1a, numerator equals 0. X cubed equals 0 means that we expect to have a 0 of 0. B, x squared minus 1 really cannot equal 0. Therefore, x cannot be, add 1, take the square root, plus or minus 1. So I check those real quickly. No conflict, no holes. I've got a 0 at 0. I've got no ability to be 1 or negative 1, so there's our asymptotes. And this is kind of fun right here. This is really a triple 0. This is really a 0 multiplicity 3, which means I expect to have a cubic looking occurrence at that 0. I expect it's either down left up right or up left down to the right. We'll see on that shortly. Okay, so a little bit of guidance in there. Let's go for C. How about when x equals 0? How easy is this? I get 0 to the third on top over 0 minus 1 on the bottom. I get 0. Oh, bummer, I didn't learn anything new. I just got that point again. At least it confirms what I suspected earlier. Now, remember this one. Not only is this a 0, not only is it a triple 0, but it is the only place, I think of it as like a doorway from the basement to the upstairs. It's the only place we can get from the basement, the bottom part of the graph, to the top. There is no way some other time I could have a curve look like this. I don't have access anywhere else through the x-axis. So you might hear me say, there is no axis through the axis. We can't get through there. So let's look at 2 now, the big test. Here's how I like to start. I've got a third degree divided by a second degree. Third degree divided by a second degree wants to look like a first degree, but a first degree is like y equals mx plus b. That's first degree. This graph wants to look like a line. There's going to be some curving going on, but if we zoom out on it, it wants to look like a line with some non-zero slope. And you could say, well, if x gets really, really, really big, the 1 becomes insignificant. It's x cubed on x squared, and it's x. And to be honest, the graph of this does want to look like y equals x. And you're going to think, maybe I don't have to do what he's about to show me here, but we have to long divide this. So this is x squared plus 0 x's, I like filling in the holes, minus 1 divides into, didn't really give myself much room there up top, x cubed plus 0 x squareds plus 0 x's plus 0. Seems like a little overkill, but this isn't going to be bad at all. X squared goes into x cubed x times, and I get x cubed plus 0x squared minus x, but I am subtracting those, so opposite, 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 and I end up with 0. I end up with 0x squareds. I end up with just an x here, bring down the 0, and I ask how many times does x squared go into x? 0. So, point I want to make here by the long division is that really this equation could have been written as x right here plus a remainder on what I'm dividing by. And now look what happens when x gets really, really big. When x gets really, really big, this matters. When x gets really, really big, what happens to this? I put in a billion. I get a billion over a billion billions. One apple to feed the world. This becomes 0. It's residual. It's residue at that point. Our equation is y equals x. And when we do the long division, our equation is going to be right here. In this case, x plus 0. So y-intercept 0, up 1 over 1, up 1 over 1, asymptote, down 1, left 1, down 1, left 1. Looks something like that. There's some more guidance for us. Okay, again, here's the trap that some of you fall into. You say, I can just look and tell this thing is just going to be y equals x, because when x gets really big, 1 doesn't matter, x cubed on x squared. Well, guess what else looks like y equals x? Y equals x plus 3 looks like y equals x. It's just a little bit above. Or y equals x minus 1 looks like x. And that's going to happen in our long division at times. Okay. So now we need a little bit of guidance, but to be honest, I don't need a whole lot. Let's talk about what's happening over here to the left. Am I in this zone up here, A, or am I down here in B? Remember, what did we learn up here? There's only one doorway through the axis. I must be down in B. If I was in A, I would have to look something like this, getting sucked into the asymptotes. But I'm in B, so I must be down in here somewhere. Probably a good idea, step 3, to get a value there. I'm going to put in -2. When I put -2 into P, I get -2 cubed, -8, on -2 squared, 4 minus 1, 3, I get -8 thirds. So at -2, I'm down 2/3, or 3/3, 6/3 to here, 8/3 down into there. Must look like this. And then when I put in +2, what happens? I get 2 to the third, 8. The denominator stays the same, 3. Oh, this is an odd function, not odd peculiar, odd odd. It spins around the origin onto itself. 2 gets me up to 8/3. 2, 6, there's 9, a little short of there. Something along that lines. Now, what happens in the middle? Here's a trap. If you're really sharp, you know we got a 000. And you say, oh, it's going to act like a cubic there. And because it's positive x cubed, it acts like a cubic goes up to the right. I got in trouble there. Let's think about this one for a moment. Let's go just a little bit to the right in our head. If I was to put 0.1 in for x, I would get a positive value on top, 0.1 cubed, over 0.1 squared minus 1. Oh, I'd get a negative in the bottom. Positive divided by negative, negative. I must be going down from here. How about if I put in a negative 0.1? The numerator would be negative 0.1 cubed. That's a negative. The denominator would be negative 0.1 squared. That's like 0.01 minus 1. That's negative. I'd get negative on negative positive. This guy does look like a cubic, but the fact that this is negative through that region, or excuse me, the whole thing is negative through that region, makes the x cubic upside down. So a little bit of analyzing. You could have always gone down to step 3 here and tried like 0.5 and see what happens. Try negative 0.5, see what happens. Sometimes it's fun to just reason through it. All right, big mess there. Okay, let's take a look at this guy. Let's just start with numerator equals 0, 1a. If the numerator equals 0, it'd sure be nice if this factors, and I see that we're in ratio 2 to 1, 2 to 1. So this guy's going to factor by grouping. I'm going to factor out an x squared, 2x plus 1, and I'm going to factor, which means if it factors by grouping, I'm going to be able to get another 2x plus 1. I can if I factor out negative 4, which means I can pull out a 2x plus 1. I'm left with an x squared minus 4. Oh, that factors. X plus 2, x minus 2. Ah, I got 3 zeros here. So if that equals 0, then I get zeros of x equals negative 1/2, x equals negative 2, and x equals 2. So I got 3 zeros at this time, provided none of those are shared. B, denominator equals 0. That factors. X minus 2, x minus 1 cannot be 0. So x cannot be 2 or 1. And there it is. Boom, boom. Hole in the graph, stars, don't want to forget about it. Got a hole in this graph. But I did pick up a couple of zeros. I got a 0 at negative 1/2. I've got a 0 at negative 2. Over at 2, I don't want to do this one. I've got a warning sign right here. I'm not going to forget as I move my graph towards 2, I have a hole in the graph. I have an asymptote. X cannot be 1. Got a lot of asymptotes at 1. X cannot be 1. So there's a fair amount of guidance right now. Not only are these my zeros, there's no other place I'm getting through 0. C. When x is 0, watch how easy this is. When x is 0, gone, 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 gone. Negative 4 on negative 2. Or negative 4 on positive 2, excuse me, which implies put in 0, get out negative 2. Isn't that nice? That's why we get that point. 1, it's a y-intercept. 2, it's a very, very easy point to get. Wow, I got a lot of guidance to the left of my asymptote. Next step. Number 2. Big X test. So the first thing I say is cubic divided by quadratic. Third degree divided by second degree wants to be a first degree. And this is where I want to make sure you don't fall in the trap of saying, well, nothing matters in the numerator except for the 2x cubed. In the denominator, x squared. Ignore everything else. 2x cubed on x squared, 2x. You're partially right. The asymptote here will be the line y equals 2x, but it may be up or down. We have to long divide. It's not that bad. X squared minus 3x plus 2 into 2x cubed plus x squared minus 8x minus 4. And x squared goes into 2x cubed. I know my answer is going to pop up right here, the linear term. X squared into 2x cubed goes in 2x times. And I get 2x cubed minus 6x squared plus 4x. But I'm subtracting those, so I like to go opposite, opposite, opposite. And I get 0 x cubes, and I get 7 x squareds, and I get minus 12 x's, and I get down, bring down a minus 4, and I say x squared goes into 7 x squared plus 7 times, and I am done. Yes, there's going to be a remainder, but the remainder is going to be that residue that I mentioned. So we need an asymptote, y equals 2x plus 7. 1, 2, 3, 4, 5, 6, 7. Wants to go up 2, right 1, or down 2, left 1, down 2, left 1, down 2, left 1. Something along that line is our asymptote. So I'm going to invade my space up here. Something down here. Well, I couldn't ask for any more guidance to the left. I've got 3 points in region A. I guess the only thing I want to know is this 0 right here, is this a touch point where it goes back down, or does it pass through? But that was just a single 0 right here, so that is a pass through. Likewise, single 0. So there we go. The next question, what happens to the right? And the temptation then is, well, I guess I'm going to build a T-chart. I'll put it over here to the right. X, Y, and I'm going to put in the value 2. But remember what happened at 2. That's my green arrows helping me out. At 2, we have a hole in the graph. No sense in testing 2. So maybe we want to test 3. So when I test 3, I'm going to give myself some room up here. I'm not going to forget that hole, but I'm still going to leave it up there. When I test 3, I get 3 to the third, 27 times 2, 54, plus 3 squared, 9, minus 3 times 8, 24, minus 4. Let's see, that's 30 plus 9, 39, 35, on 3 in the denominator, 9 minus 9 plus 2, on 2, 17 and a half. Where was I? 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and a half. When I'm at 3, I'm up at 17 and a half, somewhere up in here. How was I certain I wasn't down here in region B? If I was in region B, then I would have had to get sucked into these asymptotes. And again, I had no passageway over here. So that would be no good. Okay, what did I forget? I just erased my green arrow mark, and boy, if I don't do that a lot. There is a hole in the graph at 2. Okay. All right, well, I hope that helps. Again, reminder, you can download the notes to this, and that would be at, if you Google Purple Shirted Nerd, one word, go to the Hananiga Pre-Calculus page, and look for Chapter 2.7. It's downloadable. The notes are there. Hope this helps. Good luck to you, and stay tuned.